Three questions involving work. Now, work itself is a fairly easy calculation. It's just force times distance, but we've got to be careful with how the question is worded. If we look at question 1, we've got a guy named John pushing on a car with a force of 400 newtons. After a while, he ends up pushing the car 5 meters, and we want to know what is the work that John does on the car. So to find the work on the car, we need the force acting on the car multiplied by the distance over which that force acts. Well, Newton's third law, don't forget, always comes into play when you have two objects interacting with each other. The car is pushing back on John with some force F, 400 newtons, and John is pushing on the car with a force of 400 newtons. And the force we're worried about is this one that's acting on the car as a result of John's push. So 400 newtons in my picture is to the left, and the distance over which that force acts is 5 meters. And the rule for work done on the car, is the force applied to the car multiplied by the distance over which that force acts. And the rule is that those two things have to be parallel. And you can see from the picture, both my force and my distance are parallel, and in fact they're both in the same direction. My displacement is to the left as well. And if they're in the same direction, we get positive work. So all I do is I go 400 newtons and I multiply it by 5 meters to get 2,000 Newton meters, which is the same thing as 2,000 joules. And it's a positive answer because they're both in the same direction. In the energy and work world, if you get a positive amount of work, that means you've given the car an additional 2,000 joules of energy as a result of that push. Notice if I did the work done on the person, on John, the force that acts on him is to the right while the displacement is to the left. So John's work would be the same value because the forces are equal and opposite, but his work would be negative. So in other words, John is actually losing energy. If the car wasn't in his way, he would have more energy. He would be going faster. Now it also asks, what kind of work did we give the car? Well, work is a transfer of energy. We did not lift the car up. We didn't give it any potential energy, but we can assume that as he's pushing it, the car is actually going faster and faster and faster. So we have given it kinetic energy. The work done went into changing that car's kinetic energy. Question 2. David is training and doing sprints with a parachute. Pulls with an average of 150 newtons of force over 20 meters. How much work does David do on the parachute? So again, Newton's third law, the parachute is pulling back on David with some force, and David is pulling the parachute to the right in my picture with an equal and opposite force. It's the force that acts on the parachute that we care about, and that force is present for 20 meters. And we go to our work equation. Work done on the chute is force times distance. These two things have to be parallel, which they are. In fact, they're both in the same direction, so as above, we would expect a positive amount of work. 150 newtons times 20 meters gives us 3,000 Newton meters or 3,000 joules of energy transferred or work done. And again, what was the point of that? David has given the parachute some speed. So we can assume that the work done on the parachute goes into changing that parachute's kinetic energy. Now, Sonia is the last question we're going to look at, and she's doing a plank. And we've all seen planks. Basically, you just remain stationary for 45 seconds in the position that you see in the photo. She weighs 400 newtons and is holding herself up about 0.2 meters off the floor. Now again, work is force times distance, and the force she must apply to her body must be equal and opposite to this 400 newtons of weight. Maybe not exactly because she's got some feet on the ground, etc. The weight's evenly distributed throughout. But 400 newtons must be pushing up in order for her to get into that position, which is 0.2 meters off the floor. And while, yes, those two forces, that force and that distance are parallel to each other, the work done is getting to that position. To maintain that position, she's not moving at all, so there is no additional displacement. So even though she has a force, for 45 seconds she's not moving, so her distance is equal to 0. And that gives us 0 additional units of energy. Remember, work is a transfer of energy. So Sonia is doing no work, even though she's sweating and working hard. There's no additional work done on her body, as it does not change energy at all in that position.